Yeah, I was talking about what kind of companies are these which are offering these kind of salaries. I want the answer from you. That's why I'm waiting. Ah, Graviton. Good, good. Now you are getting there. Rubrik. Good. They are not tech giants. They are of a specific thing. I think somebody got it right. Sahasra Gullapalli got it right. Okay. Uh, they are called HFT companies. What does HFT stand for? Good. High frequency trading. Yeah, good. So there is this is also called algorithmic trading. Okay. So actually, as part of our university transition, we are going to start a program which is actually going to be offered first at the MTech level, but we are going to offer certificate program. So we are going to start with a certificate program uh, in certificate program is being launched in quant computing. Uh, okay. So under this program, basically it's a fintech program with uh, algorithmic trading or high frequency trading. Okay, the program will be in algorithmic trading. The basic skills are you need to know about options, derivatives, futures, and all that. We'll give you the books and all of that, and also C++ or Rust. We will start with C++. You should be extremely good in C++. It's called low latency. Okay. Now we have begun the starting of this program. In another 2-3 months, we'll offer this certificate program in quant computing, aimed at basically algorithmic trading or HFT jobs. Hoping that and then we are going to invite these companies that you are seeing, all the Da Vinci's of the world, the HFT, other HFTs, Optiver, Gravitron, all these companies which you mentioned, they are all basically HFT companies. So we're going to offer these companies to come to our campuses and see whether we can get some of you those kind of jobs. I don't know whether we'll be able to get you to the IIT level jobs, because those guys, some of the people at IITs, especially the JEE top 100 and all, they have a very good grip on maths essentially. The other thing is probability, very good probability distribution functions, and statistics. Also, very good understanding of calculus. All this is the maths part, and this is the C++ part, and this is the knowledge part. You put all these together, you get high frequency trading. So we'll show you how to do some of this. Together, we'll create some kind of mock platforms. So we are actually starting a startup thing in this, of course, also with AI and ML. This is a new addition into this high frequency trading, so that we can start. So anybody interested can approach us. This will not be open for this. We are still building. It will take us 3 months to build. Sometime in March, we will launch this, and I will keep you informed. But this is a new development that we are doing, and it was something overdue. So we had not built this department. Now we are building this department for quant computing, not quantitative computing. Please don't misunderstand here. Quantitative. This is quant computing, not quantum computing. Sorry, this is not quantum computing. Nothing to do with quantum computing. This is called quant. Quant is all this. So this is where some of the high tech jobs again. In order to specialize in this, become good. If 100 people join, I think 10 people will emerge who are good, because it's quite deep, and understanding this is very deep. Now, if you want, I can give you one textbook that you have to start reading. I'll give you the name of that textbook. So those of you, the rest of it we'll do in the program, but the entry to this program will be based on your knowledge of basically what we'll ask you to do is you should read up first options, derivatives, futures, and all of this. And I'll give you the book. There is a book by the same name, Option, Futures, and Other Derivatives, by David C. Hull. Ninth edition is the book that you ought to use. Sorry, not ninth. I'm sorry. 11th edition is the book that you need to use. Okay, David C. Hull. Those of you who are interested can start reading this book, and this is your first step to really become rich. If you want 1 crore plus salaries, this is the way you have to go. It is doable. This is doable, and we can go ahead and do it. Yeah, David C. Hull, 11th edition. That is the book you will have to start reading. And in March, we will conduct an entrance test for this program. If you, the rest of it we will do. See, the probability, the calculus which is needed, the C++ which is needed. No, sorry. You will need to know C++, of course, the regular C++, the low latency C++, which is that fast C++, we will cover in the program. But you will enter the program with knowledge of options, derivatives, and futures from this book, David C. Hull, 11th edition. Oh, sorry. Not David, sorry, not David C. Hull. I'm sorry. This is John C. Hull. Sorry, not David C. Hull. It is John C. Hull. I'm sorry. Yeah. So you wrote that?
Yes.
Okay. It's John C. Hull, not David. So John C. Hull, 11th edition. That is the name of the book. And Hull, not Hulk. Huh? It is Hull, Hull. So that is the name of the book, and we will conduct the test, the entrance test, because I don't want anybody and everybody to come into this program. You will be wasting your time. This program will be charged, by the way. It's not a free program. It will be charged, and you will, because I'll have to get some external people and all of that. It's not something which you should take casually and all of that. This is serious. This is meant for serious people with serious ambition and with serious goals of getting into the high bracket of high frequency trading. And also, once we get trained for the training, the certificate program is for a year. We will decide how the calendar has to run. A year, some of it will give you exercises, some of it is case studies, all that kind of thing. It's a year-long program, 1 year program, and obviously you'll get a certificate at the end of it. But most important is you'll get ready for this kind of jobs, because we as a institution are getting ready to attract that kind of algorithmic trading jobs, so that this will add. And so this is the steps which we need to do and take it forward. Okay. So that's the goal. So hopefully the test will be based on C++ and this textbook. It's a big textbook. It's a 800-page textbook, and we will take you based on that. And the test will be in March, around March 15th is when we are planning this test. So you have 3 months time, 3 or 4 months time, 3 months time to prepare and read and get ready. And this will be the ticket to big money. Again, this is not for everybody. This is only for people with a lot of ambition, lot of goal, lot of josh in them to hit the high bracket. Rest of you can be happy doing regular work. This is the ticket to a top thing. Our job is to open the ticket. Now, who takes it or who doesn't is up to you guys. So so get ready for it. In March, the program is ready. We are already getting the professors ready from our side for offering this program and all of that. Okay. So now going back to what we are going to do today. So we will start. Yeah. So we are at a stage where we are starting the PyTorch. Now I'm going to do this. So we have finished, or in the last session, I finished showing you the basic Python program, the basic Python program with back propagation. We showed back propagation with gradient descent, stochastic gradient descent. Then I showed you how to do momentum. Then I showed you how to do with learning rate decay. We did not use a single library while doing it other than the basic Python. Oh, I like that. I'm just interrupting this. Is that test open for first years? We would love to have first years. It's not just open. We are welcome. We welcome first years because that's the right time to start getting into HFT. We welcome first years. We just don't. We are not just saying it's open. We are open with wide arms. We are waiting to welcome first years into this program. Okay. So that's the book. Yeah, options, futures, and other derivatives. Yes. John C. Hull, 11th edition. Yes. Please don't read any earlier editions. Read 11th. If a new edition is released after that, that's fine, but we will stick to 11th edition. Okay. So 11th edition is the one which we would like you to read. Okay. So we did this, and the test, whether it's first year or second year, test will be the same. You need to know C++ and you need to have studied this book. So the test will cover both this book as well as C++. So it will have both components there. Okay. We are going big shot, we are going for the going with everything into this game. Okay. Just like we are going with everything into the AI/ML game, we are going with everything into the algorithmic trading game, and you will see how we go about doing it. Okay. Okay. Now coming back to the core track of AI, we are done this in the last session. So now what we are going to do today is I'm going to do PyTorch, but PyTorch also I'm going to do it step by step. Today I'm just going to introduce PyTorch and do all of this in PyTorch. So I'm going to do SGD, I'm going to do momentum, and I'm going to do learning rate decay in PyTorch. Same algorithm I'm going to repeat, but using the PyTorch library. And I'm going to show you how that program works, where the simplification is, and how easy is it to do with PyTorch. You will see yourself. It's pretty easy once you start using PyTorch library. But there will be the next session, that is in the next Sunday. I will do another session on PyTorch with using the built-in Adam optimizers and built-in backward propagation, uh, uh, built-in auto gradient computation. All of that will be built in and done in the next session. So this session uses PyTorch, but doesn't use the Adam optimizer, which has already the optimization done. Backpropagation happens automatically in PyTorch if you use the right functions. The gradient gets computed also automatically. So all this we will do in the next session. Okay. And difference between quantum computing and quantum computer.
We understood that as
Are Baba, we are not going into quantum at all. This is quant. Mahendra, Meghna, this is nothing to do with quantum computing or quantum computer. We are talking about quant. Okay. Talking about AI, so there is going to be 2 sessions in PyTorch. This is the first session which I'm going to do today, and then I'm going to do another session next week on PyTorch, where we are going to talk about the program will be much more small, where I'll use the built-in Adam function of PyTorch. I'll use the backpropagation of PyTorch, and I'll use the auto-grading facility of PyTorch. Today, all of that will be there, but all of that will be done manually using PyTorch. The things will simplify. and all that. And now we are ready to start with the PyTorch library. So I'm making it easier for you to understand PyTorch first, and then with these options. So that's how we will do. Okay. Yeah. So okay. Now, yeah. So now let's start looking at a PyTorch program which does this. So before that, what is PyTorch? Basically, PyTorch is a library which is called a tensor. PyTorch is a tensor library. Okay, tensor basically means programming with multi-dimensional arrays, multi-dimensional matrices or arrays, and it's oriented towards doing that. You will see because of that, our code will become very simple. We'll not have to write loops. Some of the additions and multiplications will happen automatically. The coding will become easier, and you will see it on your own, how simple it is to do. Okay, so with that background, let's start doing PyTorch, and let's start looking at the code for PyTorch. The easiest thing is to understand PyTorch is to look at code which is driving PyTorch. Okay, yeah. So let's start now. Yeah, so we are going to implement using PyTorch. We are not going to use the AutoGrad facility or the automatic back propagation of PyTorch. We are not going to use that. We are going to use basic PyTorch. Okay, and we are going to do full manual forward and back propagation like the code that we have been doing. See, I'm going very slow, stage wise, and that's the purpose of these Sunday sessions, that I want you to build your AI on very strong fundamentals so that you understand things at a core level. And hopefully today we'll be doing a few exercises towards the end on a tantric to see how things are. Okay, now we are going to use two libraries. One is called the Torch library, which is nothing but the PyTorch library. It's called Torch, and the random is for random library. We are going to use a seed equal to 1. You can have any seed. This basically so that your random values and my random values are kind of same, and that's why we are having the seed is equal to 1. We are manually seeding both the libraries, Torch manual seed to this seed, and random seed to the same seed. So all the random numbers generated by Torch are going to be similar to yours and mine, because we'll both use the same seed number. And also the random which are generated directly, they will also have the same seed. So this is how the library starts. This is to guarantee reproducibility of what exercises we are running with you. I think we talked about it earlier also, and so we will now start with that. Keep following. Acha, now, do you think we should send them this code already? Just send them, no, in the chat. Acha, before going forward, I think I'll pause a bit, and because I would like you to see the code also in your own window. We are sending you the code, this code only. Yeah. This library. Oh. Don't send any other PDF. Send this. Yeah. Okay, you will receive this PDF in a moment. I'm going to just wait for him to send. You'll receive this so that we can discuss this together, and you don't have to waste your time taking out this code. So we are giving you this code straight. And this is mimicking the backpropagation code of Jason Brownlee, same way. Okay, we'll pause a minute to send the code. Okay, I think we are fine. Okay, so let's start with the. I'll also try and summarize the differences between that code and this code as we go. It's all getting recorded, no? Recording is on. Yes. Yeah. Okay. Now you can see how the initialized network looked like there, and now how does it look like? yeah, how the network initialization looks now and how simple it gets, you can see here. So now let me walk through the code. It's very easy and you should understand. So again, we are creating a 3-layer network. The input layer, the input, I draw the input like this, and the output. So this is the input where all the inputs come. Depends on the number of inputs. So this is n inputs. Okay. And number of hidden neurons, the number of neurons in the hidden layer, and number of outputs. Outputs. Here we are going to have 2 outputs. It's basically going to build an XOR as a result, but so there are going to be 2 inputs, 2 neurons here. There's going to be only 2, 2, okay. 2 inputs, 2 hidden layers. It can be anything though. So now let's ponder a little, see how the data structure is created and how it is built. If you remember in the earlier case, for each of these weights here, for each of these neurons here, we had a data structure in which there were its associated weights, that is all the weights which are connecting to this neuron. We kept track of the weights which are connecting the input to this neuron. The weights we had to keep track. Then what was a delta which was created at every neuron so that it could be back propagated. Then we also kept the output which is created at every level, which acts as an input to the next. And then we also had a separate data structure where we kept the gradient and which we could then accumulate the gradient and then apply it to the weights. So this was the data structure we had used earlier. And for us there, how was our network represented? It was represented as a list of layers, if you remember. And each layer was a list of neurons, and each neuron was represented as a dictionary with weights as one of the key fields, delta as one of the key field, and output as one of the key fields. So these were some of the things, the way we represented in the core backpropagation code, right? In the basic backpropagation code. Now let's look at the way this is implemented. But before that, let's pay a little attention to, this is called the W1 weights now, and this is called the W2 weights. Okay. Now, if you visualize, W1 weights are a matrix. So now W1 weights are called a 2-dimensional array. But now you have to understand that W1 weights and W2 weights are now matrices, like matrices. How is the matrix represented? What is the dimensions of the matrix? It is n inputs into n hiddens. Because see, for each of the hidden represented by a column here. So now we have weights which connect to this and weights which connect to this, right? These are the way the weights are. So this is one row of weights and this is another row of weights. So the way it gets represented is the number of inputs. These are the number of inputs. So if it is, so the weight matrix, the number of rows is decided by, so it's a matrix, and the number of rows is decided by number of inputs, and number of columns is decided by number of hidden. So what does this represent? What does this row represent? This row represents all the weights from this particular input to this particular this as well as this, right? So the column is represented by the hidden, number of hidden. See this, the dimensions of W1 is random matrix. It's a random matrix with what dimensions? N inputs and n hidden. That is a dimension. So the matrix which is automatically created has n inputs and n hidden as the number of columns, n inputs as the number of rows, and n hidden as the number of columns. So what will be its interpretation? Its interpretation will be each row each row represents the connections from that input, that is one input, to all the outputs. To all the outputs means all the hidden in this case, all the hiddens. So this will be this. And the second row represents what? Similarly, the second neuron in the input, how is it connected to all the neurons in the hidden layer? That weights, those weights. So these are those weights. For a given input, the column represents sorry, for a given input, that is for that row, the different columns of that row represent how that weight is, that input neuron is connected to which neuron outputs of the hidden layer, right? So that is how this is represented. So when this is very important to understand, guys. This matrix has to be understood that way. So I am creating a random matrix. I am no longer creating this kind of a data structure of arrays and all of that, or list of lists. I'm not creating that data structure because I don't need it. I am creating a much more simpler data structure which represents the weights of this matrix. And similarly, I'll have weights of, I'll create another matrix which represents the weights from here to here, here to here. All these weights I'll represent. That will be the second matrix. Then the third matrix is actually not a matrix, sorry, the B1 is not a matrix. It is just a random vector with n hidden, because n hidden, each one of them has a bias. So that is a bias which is added. Remember, the equation is W1x1 into plus B1. So this is the B1, which is not dependent on any input or anything. It doesn't change with the input also. So that is the hidden. So this is what is hidden. And W2 is created similarly from this side. These are the weights. So the whole matrix is simplified. Whole data structure is largely simplified, because if you understand this, we have kind of understood the whole work. So this is W1, this is W2. W2, the dimensions are what? N hidden, because each of this element is connected to each of the neurons in the output. So it's represented by N hidden, N output. So we are creating random number of random matrix based on N hidden, N outputs. And we need a bias for finishing that equation, which is equal to the number of outputs. That is a vector. So this is the weights and matrices that we need. So the network consists of actually 4 matrices or 4 vectors. For simplicity, you can think of them as 1D matrices and 2D matrices. So this is the weight matrix W1, which is between the input layer and the hidden layer. This is the bias which is required for the hidden layer. This is the weight matrix for the weights between the hidden layer and the output layer. This is the second weight matrix. B2 is the bias for this matrix, for this output layer. So these are all vectors or matrices. Basically, this is 2D, this is 1D, this is 2D, this is 1D. Okay. So this is how the network is represented. Now, I'm going to pause here and ask you, how does this network look? Are you have you understood this network? Because this network data structure is fundamental to understanding the rest of the code. You understand this well, and then I'll tell you the code becomes a piece of cake to understand, because then we are going to rely on just matrix multiplication of PyTorch, supported by PyTorch, to do this. So here PyTorch is only creating these random matrices, but you need to understand the interpretation of these matrices. A lot of people don't. And then we have issue. So this is layer 1, which connects the hidden to the inputs to the hidden. And that is basically the first layer. Layer 2 connects n hidden to n outputs and all that. So, and we are not asking it to create any gradients and all that, which we'll see in the next session, how that happens. So is this part kind of clear, that you have understood this part? So I'm going to pause here and, as usual, do a small poll. Have you understood this data structure, that is initializing network? Because if you are clear on that, my goal is very easy to do. Okay, we're just doing a quick poll just to check whether you have understood the data structure I just explained. Acha, most of you have understood. Very good. It's a so far so good kind of a story. Okay, we'll just wait for a couple of more minutes and then we'll continue. We go by majority, as you have figured out. So, which is what any democracy will do. How will the questions क्यों यहाँ क्यों आ रही? Abba. Can first year join the program later because we don't have much knowledge? Yeah, this program will be offered every year. Okay. How will CPP questions be in the exams? Is it based on finance? Yes, it will be. You will be asked to create an options class. I'll tell you, typically the way we intend to question is we'll create a kind of a pseudo exchange. Actually, we'll borrow a pseudo exchange, that is the backend engine, and we'll ask you to do execute a forward or a derivative trade, and then compute how it happens. We'll actually ask you to do a derivative trade using C++ on our backend. We have a backend. Actually, we have, in the sense, we have not written it. We have somebody else's backend which we are using for this course. So on that backend, using C++, you'll be asked to execute a trade. A trade in the sense derivatives trade or a forward trade or option trade, and you will make you do that trade. Where are these questions? Why are they not appearing here?
There are some of them are posted in K1.
Oh, okay. Okay, I hope that answers your question. Yeah, okay. So how's the poll?
16, 84, 80 submitted, 69.
11.
Yes.
Okay, okay. So we are kind of okay. So this is the network data structure which we have created, which consists of, so if you realize, this network data structure is a dictionary with 4 keys, W1, B1, W2, and its corresponding things is the weight matrix randomly created, or the bias bias vector, weight matrix again, and bias vector again for both the layers. Okay. This is familiar code, I'm sure. Only thing is, instead of using the direct exponent from our Python story, I'm using it from Torch. Nothing different. So this is the same sigmoid and the same sigmoid derivative also. Sigmoid derivative, as you know, if you give a parameter, it is that into 1 minus that. Output 1 minus output or anything. A derivative of a variable, sigmoid derivative of x is sigma x into 1 minus sigma x. So that is what it is. So that is a sigmoid derivative. Okay, so so output is already sigmoid x, so that's why it is like that. Okay, now we'll look at forward propagation. Now you will see how simple it is to do forward propagation using PyTorch, because we don't have so many loops. One thing you will see suddenly, those of you will are going to look at this code, and those of you who have been following me carefully in the last month or two, who have been watching my sessions and understanding those sessions, I'm sure you will know we had a lot of loops. Now you will see suddenly the loops have gone out because we are dealing with matrices. You know, matrices already has, or the matrix multiplication already has a loop in it, which now, because I'm using PyTorch library, I'm straight away being able to use the operator and do it. Now you see what we are doing in forward propagation. See how easy it becomes when I use a library, both for forward propagation as well as a backward propagation. So now, what is the input to my forward propagation? It is x batch. And what is the X batch? It's a matrix. The way I look at X batch is a matrix. How do I look at a matrix? How is my input X batch? X batch is the number of attributes which we are going to work with and number of samples. So it's a matrix. So what it means is that this is the batch size. This is the batch size. So many rows or so many samples, all in one batch. Remember, in the last session itself, we talked about breaking the entire data set into a series of batches. So this is one batch, and these are the attributes. Attributes are the area of the apartment, the floor on which the apartment is, all that. Or if you take person, the sample data that we are considering, the attributes are the diastolic blood pressure, the systolic blood pressure, the weight, the gender, all of that, family history, level of cholesterol, all of that to predict heart disease, yes or no. So basically, there are, in our case, going to be two outputs. They are going to be 0 or 1. I mean, the way I will talk about that outputs in a moment, how they are created and what they mean. There are going to be two outputs, which means that we are not going to produce 0 and 1. We are going to produce an outcome, healthy or not healthy, as an example. And so there are two bulbs. One is called a healthy bulb, other is called an unhealthy bulb. And it's going to produce, if the person is unhealthy, the unhealthy bulb is going to light up, or the healthy bulb is going to light up. Okay. And as far as my input is concerned, which is used for training, there is only one attribute at the output which says what is the result. Anyway, the example with which we are using is XOR, and I'll talk about that in a moment, a little later. But first, let's understand, because we have been seeing the code earlier, because it can work with any code. So now what we are doing, we are using Python a bit, and we are saying network. We are retrieving the W1 matrix and B1, which is not a matrix, which is a 1D vector. So we are getting W1, B1 from the data of the network. Same thing, W2, B2, we are getting it from the network. Now, what we are doing is we are actually doing the layer 1. Now here we had to do quite a lot of work, if you remember, when we had to work with data. Now here X batch. Now let's talk about the dimensions a bit. And whenever you deal with AI, you should think of the dimensions of matrices quite a lot, and that's how clarity comes. So if you now take this, you take Z1. What is Z1? Z1 is sorry. Before that, what are the dimensions of X batch? As you can see, the dimensions of batch X batch. This is X batch. Is the number of the batch size. This is the rows, and these are the attributes. This is the number of inputs. So batch size and number of inputs. Each row has so many inputs. So this is what is the dimension. So if you take that there are going to be 2 inputs and there are going to be 5 samples. So this is going to be a 5 into 2 matrix. The X batch matrix is going to be a 5 into 2 matrix. Whatever you take the batch size, this is the batch size, and this is the number of inputs that you are going to have. Okay, so this is what is the size of the batch, or the dimensions of the batch. And what is the weight matrix dimension? That depends on how the network has been created. So if your network is like this, we are considering this sample network. Remember, so we are taking 2 inputs here, 2 inputs in the sense, 2 attributes in the input, 2 neurons here, and 2 neurons in the output. These are the hidden layer. This is the output layer, and this is the input layer. So how many, what are the dimensions of the weight matrix here? The dimensions of the weight matrix are number of inputs times the number of features here, number of sensors here, or number of neurons here. So because each is connected to 2. So this is going to be a weight matrix is, in this example, going to be what size? It is going to be a 2 into 2 matrix. In this example, it is going to be a 2 into 2 matrix. That is a W1 matrix. Now, how does this come? And what is X batch is, I think, to take an example, we are going to have 4 inputs in a batch, or maybe 2. So let's take it as a 4 into 2 each batch, and say 4 into 2 is our input matrix. So 4 into 2. Now you see, we are directly multiplying it with W1. This is the at operator or the multiplication operator. This comes free if you use PyTorch. This is the reason we are using PyTorch in the first place. So this is the reason. So we are taking 4 into 2 and multiplying it into 2 into 2 matrix, because that is the weight matrix which we are using. So as a consequence, we'll get 4 into 2 matrix. You know this from basic multiplication. Plus B1. This is the B1. B1 is going to be 1D matrix. So that's just going to add to whatever this is going to do. It's just going to add that data. And what is going to be the dimension of 1B matrix is going to be the number of inputs. So it's a 1 into 2 matrix. 1 row and 2 columns. Okay? That's going to be the matrix. So of B1, because for each of the input, it has to have a vector. And then I'm going to do a sigmoid on the Z1. Just very simple. See, now the beauty is, because this is a torch sigmoid, it is taking an input vector. This is a sigmoid which is working on torch. This is a torch sigmoid. It's just taking the matrix Z1 and straight away doing the sigmoid on Z1. Otherwise, I would have to do this also in a loop. Okay, now this is easy. And now if you see layer 2, so the output of the first layer is A1. Okay, the first layer, in the sense, the hidden layer output is called A1. That is what the hidden layer produces. That is after doing the linear and the non-linear. Non-linear in terms of sigmoid, linear in terms of this. See how easy it becomes. No longer any loops, all that complicated coding is gone. That is the whole reason we are introducing it to you this way. Because somebody asks you why you use PyTorch, you should say immediately that because it supports this matrix multiplication and all the functions using matrices. So now it is able to get this Z1, A1. Now see how it is able to get layer A2 also. A1 is the output of the first layer. Take it and multiply it with the weights of this layer, that is W2, and add B2, which is 1 into 2 again. So add that, and then just do a sigmoid of Z2, and you get A2. So in just 1 minute or 2, without too much looping or anything, we have got Z1, we have got A1, we have got Z2, we have got A2, and we have got now we are caching the result so that we can use it for backward propagation. See the way the cache is being built, so that earlier we had to store it in that data structure, those deltas and all. Now see how easy it is. Can we see the cache? We scroll down. Yeah, you can see the cache which we are putting. So in the cache we are storing the original X input which we got, then the Z1 which we computed, and A1, Z2, and A2. So A2 is the final output that we computed. All of that we are having in the cache, and we are returning the cache. So basically, one shot we have got the output with such a ease of multiplication of the matrices. We have got the code for which we had to write loops, for doing the matrix multiplication. Here, thanks to PyTorch, we are just able to multiply and get the answer. And further, we will see later that this code can be sent to the CUDA, and the thing will happen on the CUDA also if you want. CUDA means on the GPU if you want to do. Okay, so now I'm going to move forward and show you the backward propagation, and then I'm going to just show the backward propagation for a minute, and I'm going to hope that some of you understand it very fast so that we can move forward. Okay, so this is forward propagation. Now I'm going to try and see if I can get the entire back propagation on the screen. Yeah, here is the back propagation code. No, not the entire. Anyway, you have the code for back propagation. You look at the code for back propagation and tell me, have you understood that code? I'll pause here for a few minutes and ask you this. Go to the backpropagate code, backpropagate error code, and you can see how simple it has become. No more loops, no loops at all, no for loops, no list kind of thing. Look how simple the code has become. And I'll grab a cup of tea while you're looking at it for 2 minutes, and then we will both look at what is happening in backpropagate error closely, and understand that how the libraries have simplified our work, and appreciate that. And then remember, in the next week, I'm going to show you one more level where we simplify this. Even the backpropagation will happen automatically. Here, the backpropagation is being done manually, but using library, but it is done manually. So I'm going to just give a pause, and we will just keep quiet for a few minutes. And I'm expecting you to look at the backward propagation code, which I have on the screen and which is also there with you. And we can go ahead. Okay, just look at this code and tell me how much you have understood. It's very easy. It's the same backpropagation code, but done differently. You will see there is not a single for loop. We don't need it because automatically it is taken care by the library. Okay. Now I'll go through the code, and let's hope some of you would have understood this backpropagation code, and then let's check whether how many of you have understood. Okay. Now see, I have the weights which have been populated in the network. This is the the input first weight matrix, second weight matrix, and then we also, during forward propagation, this has been populated during forward propagation also, and during initialization actually, and then during forward propagation, this is done during initialization, and we have calculated the input x, and we have in the cache A1. Cache is also like a dictionary. It's a dictionary. Network is a dictionary. Cache is also a dictionary. We have A1, which is the output from the hidden layer. A2, which is the final output. Now we are taking the DL by, see, this you have to understand is dou L by dou A2. That is determinant of loss with respect to this is A2 minus expected. You know this. This is A2 is nothing but O2. In our earlier equations, we had this as O2. The final output minus the expected output, which was there. So that is how A2 minus expected is computed. You remember why A2 minus expected? Because our error function, you remember, is 1 by 2 y bar, sorry, y minus y bar the whole square. If you take the derivative of this with respect to y bar, you will get something like this. Dou L, dou loss. This is our loss. If you take the derivative with respect to dou y bar, you get actually this. So you get y bar minus y. So that is what is called y bar minus y. So this is what you are getting. Okay, this is y bar minus y, or A2 minus the expected value. Y is the expected value here. So this is the expected value. So we got that derivative. Then this is dz2, which is the derivative of A1, sorry, of dz2 with respect to dou L2. So this is dou L by dou z2. That is the derivative. That is after that is before the activation function was applied. Whatever is there, that is called z. So dou z2, dou L by dou z2 is dou L by dou A2 into dou A2 by dou z2. A2 is nothing but the sigmoid, so it's the sigmoid derivative of A2, whatever it is. We know what it is, A2 into 1 minus A2. That is what is the sigmoid derivative. But this is how we get the previous phase, dou Z2. Now, okay, let's pause here and ask you, what is this dou Z2 represented as in the backward propagation? Let's see. In backprop, the original backprop, how is this dou Z represented at the first layer? What do I use to represent this? We don't call it dou Z2, though it is dou Z2. We use something else to represent that. Good. Excellent. These are the guys who are going to go forward. Good. That is delta. Excellent, guys. No, honestly, I didn't expect. I didn't expect it.
Just are they either from first year or second?
Achha, the guys who are answering, are they from first year, second year? Our people want to know.
60 or so.
For example, who answered first, I will show you. I'm curious. Vaishali, are you from first year or second year? I'm just curious. It doesn't matter. Second year. Okay, fine. Good, good. The way you understand all this will help us see that you understand AI well. Okay. Now, yeah. Now I'm going backward further. Okay, I'm doing the back propagation further. We have reached delta. Now we are going backward again. So we are taking the now we are at a position to calculate the gradient for W2, which is you take the delta up to that and multiply it by the input. Now you have a funny situation. Your A1, what are the dimensions of A1? The dimensions of A1 will be, see, how did you get A1? A1, yeah, anybody quickly, what are the dimensions of A1? It is batch times something. Batch into, what are the dimensions of A1? No, write it there. Yeah, can anyone tell me what are the dimensions of A1? You can go back and check in forward propagation also. What are the dimensions of A1? No. Don't tell me like that. Tell me like batch, like X batch type, so that we are clear. Don't take a specific problem. Take in a generic way and tell me what are the dimensions. Batch times which neurons? There are neurons everywhere. Is it batch times input? That is X. Output won't come. Batch times what? Weights, yes, here. Batch X weights. See, there. First of all, is A1 a matrix or not? Is A1 matrix? Yes, good. Now tell me the dimensions of A3. Good. Good. So the dimensions of A1 are, now this is very important to understand AI. The guys who understand AI will always look at dimensions. And the day you start understanding dimensions, your AI will start making sense. Please, I want to stop here and tell you how important this is that you follow the dimensions. When you get lost in dimensions, you will never, ever understand AI. Okay? You will be a very casual AI guy. Okay. So A1 dimensions are batch into n hidden, I'll say. Okay. Batch size into n hidden is the dimension of that. Okay. Now, what is the dimension of dou Z2? What are the dimensions of dou Z2? Anyone? Dimensions of dou Z2. Remember, we are dealing with matrices. Batch into n outputs. Very good. It is batch into n outputs because it depends on output. Okay. Yeah, batch times n outputs is the dimension of Z2. Z2 dimensions are same as A2 dimensions, isn't it? Just a derivative. Yeah. Okay. Now, because of this, what is happening? Now we are getting the gradient which has to be applied to W2. We will not apply the gradient right away. It depends on whether we apply the gradient now or we apply the gradient later. But we are getting the gradient which has to be applied to W2. Now you have to multiply this with this. The input with dou Z2 will give us, that is with delta, when we multiply the input, we get the gradient for W2. Of course, you also need to multiply it by the learning rate and all of that. Let's keep that aside for a moment. But the basic thing is the gradient which has to be applied to L2, W2 is this. Now, how is this gradient computed? This gradient you can't compute like this, right? You can't multiply these two matrices. So very often what you do, not very often, to need, you'll have to take the transpose of this. So A1T dimensions will be n hidden times batch, right? Those will be the dimensions of this. So when you take the dimensions of that and multiply that with this, you will get the dimensions of gradient W2 as n hidden n outputs, which is same as dimensions of the W2 matrix. Okay, n hidden n outputs is the thing which you will get as gradient W2. Okay, so now isn't this the same dimensions as W2? Yes, it has to be, because the gradient has to be applied to each weight. So this is the gradient matrix. This is the gradient matrix. It contains all the gradients which has to apply to all the weights of the W2 layer. That is the second layer. Then gradient B2, or automatically we have to do the same across the dimension 0. This is consist of the number of outputs. That, because see, we have to take the gradient and apply it. Don't worry too much about this. Okay, this is straightforward. Now we move one more level back. Okay, again the same story goes back. Now you see what we are doing. So what are the yeah, so now we have to apply the we have to take the thing out back via the W2. We have the, this is delta. You remember we had to take the weights back from delta using the weights of that layer. We had to compute the delta for the earlier neurons. Remember, these are the delta for the earlier neurons. Of course, this is not really delta. The delta comes here. Okay, when we multiply it with the sigmoid derivative, that is dou Z1 will be delta, but we are carrying the weights back. So to the dou A1, we are taking the weights back and then multiplying it with the sigmoid derivative. Now, what are the dimensions of this? Remember, dou Z2 dimensions are batch into number of outputs. And what are the dimensions of W2? N hidden into n outputs. Into n outputs. That is a dimension of W2. So if you take the dimensions of W2, you obviously can't multiply this with this. So what you have to do? You have to take dou Z2, which is batch into number of outputs, and multiply it with the transpose of that. So it is n outputs into hidden, n hidden. Okay, that is, you have to take the transpose of this. It is n output into n hidden. That is a transpose of this. Now you have to take it and make carry the weights. These are the deltas which are there at the output layer neurons. Now you have to take those deltas back into the hidden layer so that you can then compute the deltas of the previous layer. So you're carrying the weights back, you're carrying the deltas back. So you multiply with W2 into T, which is what I'm showing. So DZ2 is n batch into n outputs, and W2 is n hidden into n outputs. Now we are multiplying with the transpose. So this is n outputs into n hidden. This multiplied with this will give you, I'm writing over this so that it becomes easier. So this is n outputs and n hidden. So it will become batch, n batch into n n hidden. Okay, it becomes batch into hidden. That is what this will come, which is what we want as DA2. because batch and n hidden, that will be the number of outputs at the hidden layer. These are the outputs of the hidden layer. Batch into n hidden, these are the outputs of that layer. So at W2T, and then this is the layer delta at the first layer, which is we have to multiply the dA1 into the sigmoid derivative of A1. So the dimensions don't change because we're just multiplying it with the sigmoid derivative of A1. So this is delta 1. This was delta 2. This is delta 1, which we have now got. This, if it is multiplied with input, we'll get back the original. Okay, we'll go there, but we have now applied this. So we have not computed grad W1 yet and grad B1 yet. We'll get that in a moment in a similar way. So this is the delta. Once we get the delta, if you multiply it with its input transpose, we'll do something like this, and we will get the gradient for W1. Okay. Okay. So now I'm going to go little forward. Reason for transposing is to enable to multiplier. Very simple. Without transposing, I will not be able to multiply. Okay.
Clear this.
Clear the screen. There you are. See this. Okay. I think you will now understand this part. So same way, this is the delta. You multiply it with the input. You will get this. You know that this is also very easy to do. Dou Z1, this is the delta 1, delta at the output first layer. This is the delta at the first layer. Multiply the delta with the input, you get the gradient to weight 1. So this is the gradient which has to be applied to weight 1. And this is the gradient which has to be made to B1. Don't worry too much about this. Just focus on these. That's important to understand. Okay. So now we have got the gradient W1. But you see how easy it was to get, because what is the dimensions of this? This was n batch. If you remember, dou Z was n batch into n hidden. Okay. This was the dimensions of this. XT was n batch into n inputs. Now I can't multiply this, so I do the dimension. I do the transpose of this of the input and multiply it with the delta. So I get this transposed. So it becomes n input into n batch. And this matrix dou Z delta matrix is n batch into n hidden, because it is there for every hidden thing. So this batch and this batch cancels, and then I get n inputs into n hidden. So this is what is the thing. Forget this. Don't worry about too much about this. So we get the gradients of all the inputs, of all the weights. W1, B1, W2, B2. Now I'm hoping that you have understood this, looking at the sense of what we did in the earlier regular back propagation. I'm assuming that you have understood this part. That is, how did we compute the gradient matrices? Now these are matrices. The gradient matrix for weight W1, the gradient matrix for weight W2. If you are clear about that, that is fine. I have a question. What is the difference between the back propagation of dA1 and gradient of W2? See, gradient of W2 is the change which we are going to do the gradient to the weight. And dA1 is basically the weights which are carried. Sorry, the delta which is carried to the that layer's input. Because A1 is the input to the second layer. So we are carrying the input to that. And then once the input is carried and multiplied by the sigmoid derivative there, we know the delta at the first layer. So that is the difference, if you will. My reading is, if you get this part of the code, you will be a big guy in AI one day. If you get these matrices and the dimensions of these matrices and what's really happening here. So now I'm going to pause here and ask you this question. that have you understood this back propagation from a matrix perspective, how it has happened? Okay, we are going to rub this off and do a small poll. Have you grasped the back propagation in matrix form? Remember, this is with the presumption that you have understood the back propagation. This is assuming that you have understood the back propagation with respect to the old one, earlier one. If you have understood that, you should be able to translate that understanding to this understanding. The question for you is, have you grasped the back propagation in matrix form? Yeah, that's a good question. I'll pause here, wait for a few minutes, and then we'll continue. You just have to translate whatever we have learned earlier and think in terms of matrices and dimensions. Oh, I'll come to that. Why do we have Z1, Z2 in cache? 48 votes we got. Okay, I think a lot of people have got it. Okay, there is a question, and let's see now. I think some of you are still confused whether you understood or you didn't understand. That's also a good confusion in, Jai Telangana. Okay. Okay, I'll answer that question and we'll move on. Okay. Can we go back to the code? Just a minute. And yeah, see, in the cache, we are keeping X batch, our input, which we need for calculation. And I think the cache is also needed because we are doing it in the forward propagation, we are computing it. Oh, we are not using the Z1, Z2. You are right, actually. Here we are not using the Z1, Z2 at all. So do we need it in the cache? Good question, good catch. Because see, we are not taking the Z1, Z2 into our equations directly. We are using A1 and all of that. Good catch, Ahmaduddin, Mohammad Ahmaduddin. We may not need Z1 and Z2 in the cache because if you see in our backward propagation, we are not utilizing it and we are unnecessarily capturing it in the cache at the forward propagation time. Now, can we think of a situation where it might be needed? No, actually no, because all the equations are based on the simple derivatives. Okay, let me park that question. It doesn't look that we need Z1 and Z2 to be kept in the cache during forward propagation because the backward propagation will be driven more by A1 and A2s rather than and the deltas and all, which are anyway computed. So they are not brought from the cache. So we perhaps may not need it. Okay. Right now, I think they appear superfluous. Now, will they be needed later? I don't know. Okay. I don't think they'll be needed. We can get rid of them. Okay. Now, see, what is happening is now at all, one intuition, the matrix is being done for a batch entirely. So, we are saved some work called accumulate gradients because, if you remember, in this code, you will not see the code for accumulate gradients. Okay. The reason why the code will not be there for accumulate gradients is what was accumulate gradients doing? The back propagation was computing the gradient, and that we were doing for every sample. And then what we were doing is for all the entire batch, we are writing a loop where we were adding, appending to the gradients every time, right? So basically, we were computing the gradients for the entire batch, accumulating them. Now, when we are doing the matrix multiplication, automatically the gradients are accumulated for that way automatically, because when you do matrix multiplication, you know how matrix multiplication happens, right? You have inputs, you have hidden, so automatically the weights are being computed there automatically. the addition is happening. Okay. I think this requires a little bit of explanation. Let me try and elaborate how the matrix multiplication is benefiting. See, when I am doing a multiplication as against when I am doing at a very core level, see what were my weight gradient computed. My weight gradient matrix is now a matrix. Weight gradient is a matrix now. So as of now, how do I have it? I have it, for example, W1, I have n hidden, n inputs. My weight matrix is n inputs. That means for each one of the input, I have, and for each one of hidden, because the hidden layer is the next. So this is n hidden. These are the dimensions of my weight matrix, W1 matrix. My W2 matrix, how does it look? My W2 matrix is, again, n hidden and n output. This is how my W2 matrix looks, depending upon the dimensions of the weights which are required at that layer. W2 weights are n hidden, n output. W1 weights are n input into n hidden. Okay. And when this weight has been computed, how has this been computed? It was batch into n inputs. That was my input. And then it was again batch into n hidden. That multiplication, remember, happened, and then this was computed, right? So while computing this weight, already then we took the transpose of this. Remember, we took n input into batch because we transposed the input matrix and then multiplied it with this. So while we were doing this, you saw the batch computation is already performed when we got this weight. And because the batch computation is already performed, we don't have to do the summation across the batch. The batch, when we got this weight, it is automatically the accumulated gradient across the batch, because the multiplication happened keeping the batch in mind. And by the very definition of matrix multiplication, how does this happen? You know, this transpose into this, we take n input into batch, multiply it. So these are the number of rows, these are the number of columns. We take each one of this and multiply with the hidden. So the batch has been already incorporated, and this value that I see here is not a single gradient, it is an accumulated gradient. And that is very important to understand. Each of these values which I see in my gradient matrix is an accumulated gradient. I don't have to accumulate gradients now for the entire batch like what we were doing earlier. It has been already done thanks to the matrix multiplication. This has been already multiplied and the gradient has come here using batch multiplication. That means it's an accumulated gradient for the entire batch. We don't have to do that any longer now. Like what we had to do when we were doing it by ourselves and we didn't have the benefit of the matrix multiplication which this permitted. So I think the bottom line is you have to understand that the matrix we are looking at, the grad W1 matrix and the grad W2 matrix, these are already accumulated across batch. Both of these, the batch has been already absorbed and they have been summed, because when you do this, you know how the row gets computed, right? It takes each value and goes on multiplying and adding the value. So thanks to matrix multiplication, this has been already accumulated gradients for W1 and W2. There's no need. So now the argument for I hope you have understood, is that I don't need any more accumulate gradient code. That's not needed. I only need to apply the gradient with obviously taking the average and all that. There is no need to accumulate the gradient. If you have grasped this, again you have taken a very important step from the original backpropagation code to this backprop code. So thanks to matrix multiplication, we have already got accumulated gradients. Okay. Now let's go back and to the thing that we are discussing. And no, we have to go back. Oh, yeah, here. So now apply gradients. Now see what we are doing, how we are applying gradients. Just look at the code. Our network has 4 keys, W1, B1, W2, B2. Okay, as I said, don't worry too much about B1, B2. They are trivial to understand. Focus on your W1, W2, which are the real weight matrices. And once you understand that, you will get it. So now we are going to each weight matrix, and we are doing again matrix. This all matrix. This all happening in matrix space. So the parameters to apply gradients are what? Network, the gradients, which already have the gradient stored, accumulated gradients. That is a grad W, grad W1, grad W2, and all that. We have the learning rate and we have the batch size. So that's all. So this is anyway accumulated over batch. So if you want to actually do SGD, you'll have to send batch size as 1. Otherwise, it will anyway apply it to the batch. So there is no, it will automatically use the mini batch in this code. So now for key in network keys, what are we doing? You look at this code. The code is saying network key. That is, now we are updating the gradients. Sorry, we are updating the weights. Network key, because we are going through all the W1, W2 and all, weights is equal to whatever the weights are. This is before momentum and all that, so there is no velocity here. So network key is equal to network key, that minus equal to, you're seeing, I'm focusing on this equation. Look at this equation. My attention is here. Network key is equal to network key minus learning rate times gradient key. That is what this gradient key is. The gradient which has been computed on W1 divided by, because that's the accumulated gradient, we have to divide it by the batch size and apply that gradient change to the weight. So because gradient key is an accumulated gradient, so grad W1, this is what is gradient key. This will come to grad W1 and float batch size divided by the batch size, and then apply it to the weight matrix. So each weight will be averaged will be reduced, or its weight will be reduced. How much it will be reduced? Learning rate times the gradient of that weight, that is dou L by dou W1 in matrix form, divided by the batch size. This is because it's the value that I have in my matrix is an accumulated value. All this is happening in matrices. All these are matrices. That is, gradients is a matrix, network key is a matrix. Remember, because all of them are matrices. This all is happening in matrix as if it is happening in scalar. That's the beauty of PyTorch. We are able to do scalar multiplication like it will happen in scalar space. But remember, grad's key, that is grad W1, is a matrix. Network's key, which is W1, is a matrix. So this is W1 minus equal to learning rate, that is new, times dou L by dou W1 divided by, because this is an accumulated gradient, divided by the batch size. So that is what is happening here. Okay, so we have got to the point where we are applying gradients. Now I have to show you the training. So there are some small things in the training, but as far as applying gradients is concerned, this is a code which is very simple to apply gradients and trivial. Now there is a little bit of manipulation that you have to do with the data and all that. So I'll show you that, but that's not connected to understanding the back propagation. So you are pretty much done. You applied the weight update, So this is the weight update that you have changed. So this is W1 new, and this is all W1 old, which is coming, the gradient on the W1, the gradient matrix of W1, and divided by the batch size. Okay. So that's how you get the story, and you have got the change to the weight. Okay, in matrix form. Okay, great. So okay, now I'm going to I'm going to go forward, and since you have the code with you, I'm going to ask you to look at the training, see whether you are understanding what's happening here, and let's see whether we can ask you a few questions as to how it works. Now here, I'll explain the input and output, but I want you to look at it and make some conclusions, and then we will look at the code. Just look at, so your summary, your work for now, for the next 5 minutes is look at the code for train network mini batch function. Look at that function, look at the code for that function, and then we will talk about what that function is doing and how the training loop has changed a bit. It's not changed much. Only thing it's dealing with matrices, so some change, but otherwise it's okay. Okay, I'll pause here. I'm going to give you about 3-4 minutes to look at the code, and then we are going to talk about that code. Yeah, okay. So let me walk through this code and see whether you can, and whether we can make sense of out of it together. Okay, so now what is my input? So what is this doing? Okay, this is my network. We already know what is our network. It's a data structure with W1, W2, B1, B2. Our data set, learning rate, number of epochs, number of outputs, and batch. So this is the code. Now we are creating a data tensor. We are converting our data set into PyTorch tensor, which is basically taking it from whatever form it was and converting it into a see, what happens is, okay, maybe it's worth mentioning, this data set may be in NumPy form. Okay, originally it may be a NumPy but two-dimensional array, and we have to take it and convert it into a tensor, which is the PyTorch tensor. So that is what we are doing. And now if you see, the dimensions of our data are n is the number of inputs, and here we have 3 n into 3. So the number of inputs is n, so this is n, and the number of features is 3. Actually it's not 3 features, it is actually 2 features, x1, x2, and 1 feature which is a binary 0 or 1, which is an output. So the output, you will say, is here little bit of understanding. First of all, please understand our input is consisting of 3 features, x1, x2, and the third one is the output. So these 2 only are regarded as features, and this is the output. The third one is the output. The output is either 0 and 1, but I am representing the output using 2 bits. This is common. So I'm using 2 bits to represent output. Now you will say the output is only 1 bit. Why do you need 2 bit? It is basically called a concept which you need to follow at some stage or other. It is called one-hot encoding. Okay? One of the values will be hot. That's all. This is called one-hot encoding. So to give you a very simple example, if the output is 0, then this cell will be 1 and this cell will be 0. If the output is 1, then this cell will be 0 and this cell will be 1. Okay. So this is how it is called one-hot encoding. One of the bits, so for this is typically good for multi-class outputs. Here it's a binary output, but in multi-class outputs this becomes very valuable. What is multi-class output? Let's say you have to classify your input as one of the 4 things, either a cat or a dog or a tiger or a mouse. if this is the way you are going to do, what you'll do, actually there are 4 outputs, so you'll require 2 bits, but you will not use 2 bits. You'll use 4 bits. So this bit is for this bit will become 1 if it is a cat. Otherwise, this bit will become 1 if it is a dog or a tiger or a mouse. So when I have this output, what does it mean? It means that the output is a tiger. Okay. If I have, on the contrary, this output, only 1 bit will be on. So this means that the output is a dog. Okay, because this bit is on. So this is called one-hot encoding. So though our output consists of 1 bit only, actually we will represent it as 2 bits using one-hot encoding. Okay? So if 0 is the output, 0 will be represented as these 2 bits. If 1 is the output, it will be represented as 0, 1. That is, the second bit will glow. Okay, so 1 bit will glow every time. Now let's see how we are representing that and how we'll be converting that appropriately or whatever. Okay, so at some stage we'll convert it. Now I think let's move on. XOR, what is it doing? It is taking data tensor. It is taking all rows but all columns except the column number 2. So this is column number 0, this is column number 1, and this is column number 2. That is how the column numbers are numbered. So it is not, so your input is everything, all the rows, but up to column number 2, not including column number 2. So basically, it's to say that this is your input, right? Or whatever it may be. This is your input for this training loop. This is your input. Okay, so that is understood. And then what is this? This is your output. What is your output? All the rows of the batch and only the second column. Only the second column. Right now, it is not in one-hot encoding. At some stage, we'll convert it into one-hot encoding, but not now. Okay, so this is what is. So this is this part. This is Y all. And this part, this part is XOL. Your input we have broken into these 2 parts for training, because along with the attributes, its value also is coming. The output value is also coming. Okay, the dependent value is also coming. Then what are we doing here? Okay, I think we'll clean up a bit and then move on. Okay. Now we are saying n is equal to XOR dot shape 0. Shape 0 means get the first dimension. Just get the first dimension. This tells you what number of inputs. XOR dot shape 0. 0 means the first dimension. First dimension is the number of rows. Okay, the number of rows will tell how many input data samples do you have. That is okay. Now you got the number of data samples. Now what are you doing here? Now you are starting the epoch, because you have to do that many epochs. Now remember, we had to shuffle all the indices. So we are getting a random permutation in n values of n values. So a random permutation of n values will give some permutation of n values, which we want to do because we want to shuffle data. So initially, if the rows are numbered 1, 2, 3, 4 like this, we would like to shuffle these numbers up to n. So the numbers are up to n, that is up to 3. We'll reshuffle the values so that it will be 1, 2, 0, 3, something. Okay, some shuffle, some permutation. And with that, so the indices will be in the permutation, permitted or this will be the indices as a permutation. And then we'll take that and give that and get the X shuffled data and Y shuffled corresponding to that. Okay, same indices we'll use for Y. So this is nothing but a shuffled form of input for the batch. Okay, because before we have done batching, we are shuffling the data because sometimes the data is ordered in a particular manner, and that is the way. Okay, what is the use of one-hot encoding? Well, it becomes easier to classify all our loss functions. No, they become easier to write if they are written using one-hot encoding, when I'm going to show you maybe a session or two down the line, I'm going to show you what is called cross entropy and all that, where we have classification problems. I'll show you what is the benefit of using one-hot encoding, because it becomes easier to write the loss function on an output which is one-hot encoded, rather than one output which takes more values, or two outputs which take more values. It becomes always easy to use one-hot encoding while writing loss function. So it's a simplification for loss functions. That's why you use one-hot encoding. Okay. Now we have shuffled the data. We have initially, now we are ready to start the batch. So let's understand how to start the batch. But before that, okay, can we scroll up? Wait, we can scroll up. Now let's see how we are, no, we are starting to process the batch. Okay, let's do some understanding. So start is from 0 in steps of n. N is the, sorry, from 0 to n in steps of batch size. That is what it means. When you give a range like this, it goes from 0 to n. N means n minus 1. It's exclusive. In steps of batch size. This is just to break the whole data in batches. You know that. So the end of each batch we have to compute, because start will go on to end is start plus batch size. That is, you computed the batch. Now you have to retrieve all the data from the shuffled data for that epoch, which is what is it? Batch size start to end, which will give you X batch will be of size, batch size, whatever is your batch, into 2, because we are having 2 inputs in our case, only x1, x2 and y. So that is why it's 2 dimensions, right? And y will be what? Y dimensions will be, it will be a single dimension 1D of size BS. BS is basically the batch size. So as many batch size, that many outputs. Still it is in not in one hot form. It is in 0-1 form, which we have to convert into one hot form. And batch size is also equal to x batch shape 0. That is your batch size. Okay, because that's how the number of samples. Shape 0 is the number of rows. Okay, now see the way we are now converting it into what is called as one hot encoding for comparison. Again, go a little forward. Now understand the one hot encoding. See the no. Okay, now our outputs is going to be 2, not 1. Okay, because the way we have created our network matrix, sorry, the way we have created our network, n outputs is 2. Okay, so what is this code doing? Okay, it is converting batch size. It is converting, first giving you a matrix. Expected is also a matrix. It is giving you a matrix of batch size with how many outputs? Number of outputs. Because number of outputs is 2, though actually our data consists of only 1 output. Because of one hot encoding, we have 2 outputs. So our thing is 2 outputs, and so this is 2 outputs. And now you see how our expected values will be. Now just understand this. Expected values are, okay, now see, this will be torch arrange. Y batch dimensions are what? Batch with 1 or 0. Okay, but now what we are doing is torch arrange. Arrange means it will go from 0, 1, 2 up to batch size. We are taking that, and Y batch, that is that. So Y batch will be for that particular thing will be either 0 and 1. I hope you're understanding this. So depending on whether this is 0, then the 0th bit, this is 2 bits. Remember, Y batch is going to be Y batch initially is single dimensional, but when we are setting it in this way, it will become a 2-dimensional thing, because we are setting that bit of that because our expected is a 4 into 2. If 4 is the number of batch size, it is 2, and our input we are taking, and that particular value in Y batch. So it is basically we are having two cells, this cell and this cell for our output, because we are having two cells, but our output is single valued here. When we are getting from Y batch, it is single valued. So we are using it to index into this array and say if the output is 0, that bit is set to 1, or if the output is 1, that bit is set to 1. So either this bit will be set to 1 or this bit will be set to 1 for every row. So if you understand, this is a very clever piece of code where we are converting the code from, okay, I'll give you an example for those of you who don't understand, get it yet. Because it's an XOR gate, I'll give you an example how this is being trained. So it is input is 1 0 1. This is my original input. This is x1, x2, and my y. This is this y batch, and this is 1 1 0 0 0 1. You know, all of you know how XOR works. So this is the kind of input which we are training the neural network to follow. This is 0 1 1. Okay, this is the input. 0 1. Sorry, 0 0 0 is 0. This is 1. Okay, this is my XOR gate. Okay, this is how the XOR looks. Now, how many outputs are there in Y batch? 1. But now I am translating it into 4 into 2 matrix. So I'll show you the 4 into 2 matrix translation. 1 0, that will remain as it is. I mean, that we are not looking at. We are just looking at the transformation of this into a this is n into 1 dimension into n into 2 dimensions. That is what this is doing. My expected values are batch size into number of outputs. That is what it is. So initially it's 0. Once it is 0, I am updating it. So initially everything is 0 0 0 0 0 0 0 0. This is what I am starting with. My batch size is 4 and number of outputs is 2. This is what I am starting with, expected. Now what is the expected thing setting it to? Now look at this. Y batch 1, that is now which bit has to be set to 1? This bit is set to 1. So this will become 0 1. Then this is bit for this input, the thing will be set to, this bit will be 1, because see, the 0 means the 0th bit. This represents the 0th bit, this represents the 1 bit. So this bit will be 1. And for this, the output is 0. So this bit will be set to 1. And here the 1 bit is 1. So this bit will be 1. So this will become 0 1, 1 0, 1 0 again, and 0 1. Okay. I hope the interpretation is clear. This is the one hot interpretation of this data. Why? That means the second bit is 1. 0 means the first bit is 1. These are 2 bits. We are representing this is in 2 bits because the output can be 0 or 1. So 1 0. So the 0th bit is 1. So I am having 1 0. This 0th bit is 1. The output is 0. So the 0th bit becomes 1. And this is 1. So the first bit becomes 1. Okay. So this is how it is encoded in one hot encoded version of my expected output. So my expected output will have 2 outputs, not 1 output, though my input has only 1 input. This is a very common way of converting. Okay. So I hope you are clear about this, because this is 2 outputs, 4 into 2 outputs. Okay, this is very important to understand how conversion happens from conversion happens to one hot encoding. This is how the conversion happens to that one hot encoding. Okay. Now, once the conversion has happened to one hot encoding, the story becomes very clear. Okay, it's very trivial actually now. Okay, now we do this. We create the outputs and the cache as part of forward propagation, which we have already seen. So we run the forward propagation using XBatch, and we get the forward propagation outputs and cache. You can forget this. This is just to do some outputting and computing error. Then you do the backward propagation and get the gradient matrix. This gives you the gradient, which consists of, remember, W1, B1. So it gives grad W1, grad B1, grad W2, grad B2. It gives all the gradients which has to be computed, which is already summed up for the batch. This is for the entire batch. And then you apply the, see, everything is being done batch, so you don't have that loop. So then you apply the gradients for the entire batch. Okay, no, there is no chance to apply one by one because we take batch. If you have to do one by one, then you have to make the batch size as 1 and then do it. Apply gradients, and then the gradients get applied and the weights get updated. This is how the training happens. And once the network is trained, then you can apply one input and see the output. Okay, that I'm not worrying too much. So is this part clear so far? Okay. What is the purpose of cache here? Well, you otherwise you won't get what you need the cache, at least W1, W2, and your A1 and all that. You need A1, your W1, W2, which you have computed to calculate your changes to the grad W1, grad W2 to take the weights backward. Correct? You need that, otherwise you can't do the back propagation, isn't it? As somebody just said, you don't need Z1, Z2, but you need the rest of the gradients. You need the rest of the things to have the gradients. Otherwise, the gradients won't work. You won't be able to carry the weights back. Okay. Okay, so this is where I thought we can pause because the rest of it is now straightforward. Then how do you incorporate momentum and all? We can give you the code. It is there here. It's very easy. Once you understood this, you just have to add one more variable, one more matrix, and the velocity comes in. Okay. But if you're clear so far, we can proceed. I am seeing the number already drop below 100, which is fantastic. Okay. Are we doing a poll or something? So is this clear? So far, so good. No, guys who are there so far, no, they will be there to understand. Okay, I think, yeah, there is something. You are more worried about the HFT course. It will be partly online, it will be partly offline, yes. Fees will be high, but there will be some interesting stories there. The fee will be high. And it will be open to, we are also announcing it to outsiders, so we will have a different pattern. Gugum. Yeah, so new startup. Gugun is coming now. We already announced, so we will start recruiting for it. Those are a separate story. This is a separate story. You can do one with the other. When new startups, I mentioned new startups, Advait. When are we going to take them? We are going to take them in the beginning of 2/2. It's a full time. We will conduct the test first week of Jan or second week around Sankranti time. We'll conduct the test and we'll take. And once you have taken, then basically you will have to quit college for almost a year and join our internship program. No, we intend to take the test on Python actually. Because Python is what is needed for our AI. We will not do it on JavaScript, we'll do it in Python. We'll give you the syllabus for Python and also. You're ready to quit college, fantastic, you are my person. Okay. But it will be for 1 year, after that you'll have to start the finishing school. So if you are in second year, your 2/2 and 3/1 will be in internship. and then your 3-2 will start the finishing school. So your college in a way ends here. Then you work on internship, you do fantastic stuff, and then you do finishing school where you do some more fantastic stuff, and then you go on. Okay. Internship, your exams you still have to attend, Baba. Internship does not exempt you from exams. You still will have to attend all the internal exams and all the external exams. We'll give you those leaves. You still have to write your final semester exams, all of that. Only thing is you don't have to attend classes. We'll give you the material and you will have to study. And of course, work with us in various interesting projects on just like drug paradigm, robo paradigm, and all. Will accelerate that. We are adding the material science story. You'll understand how crystals work. You'll understand how the nutraceutical industry works. Lots of interest. Now we are all in applied AI. Acha, the entry will also be this program. What we have covered in this program, all of that will be asked in entry. That's why we are recording it. So those of you who have not been regular will have to go through the videos, go through them and all that. Because with Python, we'll also have this, because unless you know AI well, I don't want you to come and lay eggs there. The internship will assume that you already know ANN like the back of your hand. First years will have to wait. We don't have a plan to take first years yet. You'll have to wait for a year more. Focus on your academics, learn Python well, do all that. First years will bring in only in second year. Okay. I think we got our poll.
Yes, sir.
I think it's okay. Okay. I think we are done. So in the next session, sitting in college listening to academics makes us dumb. Yes, I agree. What is ADG? What is ADG? I don't know what is ADG. No, I'm not aware. I'm not aware of ADG certification. No, I'm not aware. No, first years we are not touching. First years we are not touching. Second year, first semester, some of you we are touching in a very light way. 2 onwards, our main thrust will start, where project school starts, and in a big way, and all the rest start. So we believe that students should do more stuff than just listening to academics. We believe in that because that's how you become smart. But at the same time, fundamentals should be very strong. No, HFT is not for first year. No, you won't be able to attend because HFT needs a week, 2 weeks of immersion programs and all of that. We also have an immersion campus where part of HFT is conducted. You want to see our immersion campus, our Goa campus? It's almost ready. Anybody wants to see, I can show you the video. March test is only for second years. Yes. Yeah. It's only for second year. Well, you can write, but we won't take you. You want to see? Okay, I'll just show you the video for our immersion campus. It will be ready from February first week. But anyway, some of the programs, some of the HFT will run there. I'll show you the video. Honestly, I don't know. Sri Saket, I don't know about this certification. I will check if you want, but it has nothing to do with us. Yeah, this is our immersion campus. You can see it there. It has about 100 seater, 50 rooms, right on the Goan beach. Actually, it's the Sindhudurg beach, close to the Mopa airport, the new airport. Okay, so this is, I think you play it again. There are some more videos which take it better. Okay, this is our own campus for KMIT colleges. This is called the immersion campus, where a bus will transport you and you can see it. So this will be part of the HFT. Some of the programs, weekends, and will be done here because some external professors will come, and they will use this. This is meant for that, for some of the advanced work. Okay. So how is it? Looks nice. Okay. So with that, why can't? When can't?
The CLA certification.
It's difficult, Baba. You will have to miss classes and all that, which I don't want to do in first year. I will have to check. I'll have to check the CLA certification. I don't know anything about it. Yeah. This is the Genesis Institute. Yes, it's also called KMIT's Immersion Institute. Yeah. So it was just ready then. Now it's fully ready. Okay. Yeah. Will you take us when you come to second year? Obviously, I will take you here if you are good enough. This is for you guys. This program is not for me. Why should that be a doubt? If you qualify, we'll take you. If you don't qualify, we'll not take you. But the test is for second years. Yes. Yeah. Agentic AI and generative AI, agentic AI is part of this program only. This program will continue into that. Acha, somebody has brought up this CLA, C Certified Associate Programmer. Who is giving this?
No, so C++ Institute is doing it. 55 questions, 70% of the passing score.
Well, we'll have to look at the quality of that exam, but it will help. I don't see any harm in taking it. How much it will help, I don't know, but should be a good exam. Any certification is a good certification for people who. Yeah. Lang chain will be there, Lang graph will be there, everything. No, yeah. Before that, yeah, the CE certification looks okay. I mean, I see nothing wrong. If you want to go get certified,
$100 it costs.
the exam cost is $300. Huh? No, it's there. Oh my God, cost is $300, $295, boss. Yeah, if you want, go ahead.
Then we should ban away classes and take us away.
Okay, good suggestion. Convince that to every one of you, every one of the other guys advice. Yeah, okay. So we will meet next week. Our agenda next week is I'm going to show PyTorch again with training. Only thing is what I'll do is I will show you how the momentum optimizer and how the decay happens without going through this back propagation, cache, collecting and all that. I use PyTorch library today, but I used it manually. So the next step is to not use it manually, to use it as a direct library where we'll not do any manual computation. The training will happen automatically and you will see how quick and fast the same code will be. I hope you understood the difference between the old code and this code, today's code. Now from today's code, we'll go to one more version. Then I think we can open up one full Sunday of only programming where you'll go to Tantric and do. Okay. Because we are not getting time to do Tantric exercises. We need to do them, but we'll get there. Okay. But because I want to build your theory into a strong foundation before we jump and do exercises. Okay. Sure. Okay. So let's meet you next week.